We're going to work on the Halohydrin reaction, which is the addition of a halogen and an alcohol group to a double bond in an alkene. And I'm going to use the same alkene I used for the addition of bromine to a double bond. And this also occurs through an anti-addition. It's basically the same mechanism. The only difference is the nucleophile in this reaction. So the conditions you would see would be an alkene, and you would have either bromine or chlorine, and this time on the bottom of the arrow you would have a solvent that was capable of being a nucleophile. Now I'm going to use water, but you could also see an alcohol or technically an amine, because nitrogen and oxygen can act as an electron pair donor. So it would be those types of solvents that you would be looking for in these types of reactions. Now again, I'm also going to change the way the alkene looks so I can see wedges and dashes. By doing that, I can see the stereochemistry of the final product without having to work real hard at getting it right, since this does do an anti-addition. So this is how I'm going to adjust my alkene so I can do the chemistry. So I'm going to redraw that alkene that we saw a moment ago. The alkene is going to act as the electron pair source in this reaction, and the diatomic halogen is going to pick up this pair of electrons. So it's basically, again, exactly the same step you saw when we did the vicinal addition of halogen to a double bond. In this case, again, the electrons from the double bond pick up one of the halogens. Now, halogens can only maintain an octet, so you're going to break the pi bond as a result of that and give both of those electrons to the halogen. The halogen that you are adding to the double bond also will bind at that moment in time. As a result of this, I make what's called the tent. It's technically called the cyclic halonium ion. And this could be done, again, with bromine or chlorine. Yeah, it looks like a tent to me with little stakes in the ground, so that's why I call this the tent reaction. So that's going to result in a bromide in the solution. Now, the solution is also full of the solvent. Now, I hope you remember what solvents are. Solvents are the molecules that everything's dissolved in. So there's lots and lots and lots of them. Now, I know that bromide is technically a better nucleophile for a variety of reasons. It has a negative charge. Water doesn't. Bromine is a larger atom than oxygen. So it is technically a better nucleophile. And it can act as the nucleophile. But water is predominant in solution. There's a lot more of it. And so it's much more likely to add to the cyclic halonium ion, or the 10. Either one of these two species can do the job. And so I'm not telling you that your bromine is not going to add. It will. It's just that it is a minor component of the solution. You're much more likely to add water because there's simply more of it. And as we've talked about previously with the addition of bromine to the double bond, this goes through an anti-addition. It's doing an SN2 substitution. So you're doing a backside attack and having the leaving group depart, which in this case is the bromine up there with the positive charge. Now this three-membered ring that you see here, again, has that positive charge delocalized through the bromine in both of the carbons. And if these carbons have different substitution patterns, the one that is more substituted will be the one that is more capable of handling the positive charge due to inductive forces. In this case, both of them are secondary, so it doesn't matter which of these two you add water to. But water adds as the nucleophile, and again, I've told you this is kind of like the mole in the camping story. He comes in from underneath the tent and adds. Now, carbon can't have 5 bonds, so you break the weakest bond, which in this case is the carbon-bromine bond because it's the most polarized bond. And it also relieves the angle strain of this three-membered ring. So this would be the order of your electrons flowing. You could again have added this oxygen to the other carbon. This accounts for the anti-addition along the double bond. And when this is complete, you can see that the water and the bromine have added anti to each other. There's still a bromide, it's a spectator ion. Okay. This is the species we have. It's technically an alkyloxonium ion. We do need to deprotonate the water, and you can use bromide or water to do this. I'm going to use water because there's more of it, and by doing so I would make a weaker acid. So I'm going to use water to do this job. But it will come in here, take one of these two hydrogens from the oxygen. As that occurs, the OH bond is broken, and oxygen takes those electrons because it is more electronegative. And you're going to result in the halohydrin, which has a halogen on one carbon and the OH group on the adjacent carbon, and they have added anti to each other along what was the double bond. Now these reactions do not proceed with any methyl shifts or hydride shifts. That's why we know there isn't a carbocation formed in the reaction, and the stereochemistry is very specific. So this is the believed mechanism for this type of a reaction. And again, you can do this with chlorine. That would be just fine.